Welcome to Illinois Energy Prof. Today I'm going to tell you about what I think could be the future of nuclear power. And that's modular micro-reactors. What's a micro-reactor? Well, it's something really small, all right, compared to the regular size reactors, which are really big. It's small, so you could make it someplace and ship it. It's small, so it could be made quickly. It's small, so it could be made very, very safely. But of course, it's small, so it makes only a small amount of energy. But you know what? You could put a lot of them in one spot. So here is the basic idea. First, like I said, you make a small microreactor core in a factory. And maybe it comes out to be about, each one of these 15 megawatts of thermal power. Whereas the standard large-size nuclear reactor or coal plant is 3,000 megawatts of thermal power. Keep in mind though, you don't always need 3,000 megawatts, right? The other thing, these are sealed. And they're accident proof. And you're going to say, yeah, right, everyone said it's always safe, it's accident proof. But I'll get to that, you'll see why. Beauty of these is that in 20 years, you just take it away. You don't have to refuel this, you don't have to open this, right? You just ship it back, return delivery. What these would compete with individually are remote areas or areas that need some electricity, like a military base or a remote mining community. And they don't need a giant power plant, but they need some reliable power plant. And a reliable power plant that does not make carbon dioxide. Okay. Now, for some details. First, how small? Well, small enough that it can fit in a truck or in an airplane. The nuclear reactor part you can deliver there. The part you take away that has all your self-contained wastes, you can take it in a regular transportation device. Most of these large-scale power plants, almost all of these large-scale power plants, are constructed on site. And that means each one is unique. These can be manufactured in a constantly controlled, improved environment where every one of them can come off an assembly line. Are they complicated? Sure. So is an airplane. And Boeing and other Airbus, they make 737 after 737. This thing has fewer moving parts and is smaller. How safe? Well, when we've talked about nuclear power before, we always talk about a containment building, right? Some large structure that goes over this with really thick walls and extra safing, cooling, and safety system after safety system. All right? The thing is that these units fit right in and come with or are built with their own containment building, which is concrete around it. And you stick it underground. And all of the wastes that are made stay inside the fuel, inside the reactor. So you never have to open this, and there's no need for refueling or removing the wastes. What's next? How can you actually do this? How does this work? Why does this work? And I'll tell you, the thing why this works is that the fuel is the key. So let me just tell you a little bit more about the fuel. The fuel. The fuel is called TRISO, and that's an abbreviation, of course. All right? Tristructural isotopic particle fuel. If you look at that scale there, these things are the size of a grain of sand. That's really small fuel. We take that grain of sand And by the way, the inner part of this is a ceramic fuel, something that doesn't melt to extremely high temperatures. And we take this fuel, and first we coat it with a carbon layer, because we are going to need a moderator. And that carbon layer is a little spongy. So if there ever is an expansion or some fission product gas is made, it all stays in there. Then it has a sealing layer, silicon carbide. It's like diamond. And this stuff encapsulates it. And then some more carbon. So we have these tiny little fuel pellets, smaller than a grain of sand. And this is amazing fuel because it doesn't melt. Or at least it won't melt at any temperature you could ever get up to. The advantages: it's small, it's solid, stable at very high temperatures. And the fission products, right? That's the thing that uranium splits into. Those are your high-level wastes. They stay inside this tiny grain of sand. And even if gases are produced, they stay inside this tiny grain of sand. But the amazing best thing about this fuel is called the negative temperature reactivity. If it gets hot, it stops working. Now, you might say, Professor Ruzic, that sounds like a pipe dream. But you know, this type of stuff has been around forever. At the University of Illinois and many other places across the country, there were these training reactors built in the 1950s. And when I came here as a young faculty member, and of course I came with some plasma background, so I didn't know anything, and they bring me up to the top of the reactor, and the reactor operator presses a button and blows the control rods out. You hear a loud bang. That wasn't anything nuclear, that was just the air, compressed air, pushing the rods out, and the power goes way up. And you can tell that because you can see the Cherenkov glow of the blue light as you're looking down in the pool. And you're thinking, oh my God, you know, what did they just do? But I was a little smarter than that. Because that reactor immediately shuts itself off. That's why we could use it for training. Press any button you want, you can't hurt it. It's got a negative temperature reactivity coefficient. To really get into this, make sure you understand. Let's talk about the nuclear reaction. A normal nuclear reaction, you got U-235, and you're going to hit it with a slow neutron. You get the fissions if you have the slow neutron. And this goes into two halves, fission product 1, fission product 2, okay, plus neutrons. You know, maybe around 3 more neutrons that are fast. And you have to slow those neutrons. You have to moderate them, and then you can have this reaction take place again. So we need a moderator. We could use carbon, we can use water. And the fact we don't use water in this type of reaction is a big plus. Which, if you're thinking back to a Chernobyl video, you're saying, well, wait a minute, I thought no water, no moderator, isn't that great? We have a different way of being great. If we get too warm, we get no fission reactions. Why? Because of the way the neutrons in this type of fuel, at this type of power density, behave if the temperature gets warmer. So, to understand that, we need to talk about cross-section. And cross-section is this chance of a fission, okay? Or some event, it could be an absorption, okay? Or it could be a fission. And we have to do this versus the energy of the neutron. All right? And the general curve, and this is a log scale, right? So maybe this is 1, and this is 0.1, and 0.01, and 0.001, all right? So we have this, and generally these curves look like that. The fast neutrons here at 1 million eV, and the thermal ones here down at 0.03 eV, right? These make fissions, these get produced. This is our standard moderation thought. But if we really look at these curves, you will see there's a bunch of little resonances in here. And they're very thin, and it's some interesting physics, but usually doesn't cause us much problem. Let's take a look at those for real. So here is the real curve. I got some colors on here. And what we say when a resonance gets broader, one of those real kind of hashy-like bright lines, normally they're really thin. But if the fuel is warmer, that line broadens, all right? And what this means is there's more of a chance for the events to take place. The red and the blue lines are absorbing the neutrons by the fuel, not to fission, but to take U-235 plus a neutron and make U-236, which just sits there. It's not fissile. There's a black line in that drawing, and that's the fission line. Now you can see when you're way down here at the thermal neutrons, yeah, fission wins, right? But because if we have these broader resonances, which happens naturally if the fuel gets warmer, you don't have fission winning. You can't get any fission if the temperature gets hotter. And this doesn't rely on a safety system. This doesn't rely on an operator to push the right button. This happens because of the laws of physics. Now, there are some additional safety features about these reactors, which is pretty cool. The cooling, it's passively safe. Oh my God, someone interrupted the cooling loop. Who cares? Air will cool it just fine. So that's the other thing. We can cool this with a gas. And the beauty of cooling it with a gas is the gas doesn't change phase. If I cool it with water, water turns into steam. Oh my God, I get all that pressure, rupture pipes, does things, phase changes are difficult to deal with. With a gas, it can just keep getting hotter and hotter, and that also means we can get higher thermal efficiency. The other thing is, because these reactors are small, their power density, in addition to their power, is dramatically lower, which is another reason that makes it so much more passively safe. I want to give you an example of these from a company called Ultra Safe Nuclear Corporation. And they were very generous on letting me utilize their slides. They're not the only company that makes modular micro-reactors, but it's the one that at least has helped me out here. So let's look at their fuel. This is that triso fuel I talked about. And they have even a fancier way to coat it even more. And then they pack them into pellets, into rods, into module things, and eventually they make a reactor core. It's interesting. This is in some ways about the same size as the 3,000 megawatt core, and you can see why it's so safe, because all of this is only going to be making 15 megawatts of thermal energy. And then it very conveniently goes in a unit with a self-containment building and with all of the heat transfer loops. So, not only is you have the safety of not having a phase change, we've got the stuff in the red here, right? The stuff up here. This is a molten salt loop. And you might say, why is that there? You know, ultimately, we're going to run standard generators on steam. We don't want steam to go into our reactor, but we already have the helium loop. But you see, this is part of the genius of this type of design. Making electricity is all well and good, but sometimes all you want is heat. And this molten salt and that big red storage tank can store it for when you need it. So let's say you're trying to heat a whole bunch of buildings, and it's warm during the day and cold at night. Run your reactor, keep storing that energy in the molten salt, and maybe not run it through a generator to make electricity, but run the steam lines to the radiators in all of the buildings. We skip all of that loss of thermal efficiency when you try to convert to electricity. The molten salt will also work for process heat for factories. Hey, we need to smelt steel or something, and we don't need the power on all the time, just when everything's in the bucket. Everything's in the bucket. Use this technique to get your stored thermal energy. The layout of a plant is fairly straightforward. The first yellow buildings are the reactors. You've got the heat transfer stuff, the salt storage, the generators. And I want to point out something else. Air-cooled condensers. Every time we've talked about major size power plants, the giant power plants, okay? Those power plants always had to be built on a body of water, a lake, a river, an ocean, because you had to condense the steam back. You need some outside cooling source, which then you had to put through a cooling tower, right? But here, since our power densities and our overall power is lower, we can do this with air-cooled condensers, right on site. This does not have to go on a body of water. Is this too good to be true? No, it's not too good to be true. It's all true, but it's expensive. And anything in this series of lectures on my website has told you you've got to do an economic analysis. So, economy of scale really works. And if you have your 1,000 megawatt electric plant, its price can come down to approximately fossil fuel prices. These are clearly going to be more expensive. Remember, natural gas can be about 2 cents per kilowatt hour. That doesn't count any credit or cost for the global warming impact, the CO2 impact, the methane leaking out of the wellhead impact. Conventional nuclear power might be more like 3 cents per kilowatt hour, making no CO2. And this type of system, at least the first ones, are a lot more expensive, 25 cents per kilowatt hour. Now notice, if you make a factory and you turn them out, they will go down dramatically in price. The very first 737 or the very first Boeing jumbo jet or whatever you're picking, I'm sure cost a lot more itself if they were only going to build one of them. But you see, it's not a competition with this standard grid power. The thing we are going to compete with here is going to be something like diesel generation. And in a remote area where the only other choice is to burn fossil fuels on site, this becomes actually much more economic. You can see that the yellow things here are US Nuclear's predictions of their costs, and fossil fuels really depends on what the price of diesel fuel is, right? But that can be very large and dramatic. And even at the lower prices, this is competitive. And the beauty of it is you're making no CO2. And if you think about places that can use electricity, sure, solar, wind, we have lots of those choices. But for district or process heat, there is no choice other than fossil fuels. How do you get enough power density to melt steel? How do you get enough power to run a large collection of buildings like a college campus and heat it in the winter at night? This type of microreactor is ideally suited, not just in its performance, but also in its size. You need 15 megawatts of thermal load, buy one. You need 45 megawatts, buy 3. So, this system, modular micro-reactors, are likely to be the future of nuclear power because it checks off all of the boxes that you need. And in the future, it's not as far away as you think. Ultra-Safe Nuclear plans to build the first one in Canada, which will be finished by 2024. and the amount of time it takes to build these is small, a year or so, not the 5, 6 years, 8 years that the major power plants take. In addition, in the United States, the Department of Energy is sponsoring a competition right now to build some kind of micro-reactor in the US as a demonstration plant. And that's what you need to know about micro-modular reactors.